All right, chemistry, this is part 2 of your video lecture for chapter 6, section 5. Last time we talked about Vesper theory, and how it is used to predict molecular shapes. In this video lecture, we are going to look at hybridization. We are going to finish up by looking at intermolecular forces. Let's go over the objectives for this lecture. First, I want you to be able to describe the formation of hybrid orbitals. Describe their formation. Know the shapes and hybridization of octet rule violators. And draw resonance structures as required for various molecular and polyatomic species. And explain molecular polarity, dipole-dipole forces, hydrogen bonding, and London forces. How and why do these affect the physical properties of substances? And lastly, predict the percent character of various hybrid orbitals. Now, it sounds like a lot. It's pretty interconnected, so let's get started. We're going to start with hybridization. Okay? A hybrid occurs when two things are combined and the result has characteristics of both. For example, a hybrid car like a Prius or something like that. There's a number of hybrid cars on the road right now. It uses both gas and electricity for the source of its fuel. Now, during chemical bonding, different atomic orbitals undergo hybridization, and that is what we will be referring to in this portion of the lecture. So let's look at an example. Carbon's hybridization. Okay, consider methane, for example, CH4. The carbon atom has 4 valence electrons with the electron configuration helium 2s2 2p2. You guys know this. You can already do that electron configuration. So if we're going to predict the number of bonds formed by a carbon, you'd say 4. You'd say 4 because it has 4 valence electrons, 2s2, 2p2. However, when we draw the orbital notation for carbon, we see that the correct orbital notation suggests that we can only form 2 bonds, because notice in this 2p, these 2p suborbitals, there are only 2 unpaired electrons. And remember, it is in fact unpaired electrons that can form bonds. Carbon only has 2, but we've been talking about carbon this whole time as being able to form 4 bonds. In order to form 4 bonds, carbon's going to have 4 unpaired valence electrons. And so in order to have carbon act like we've been saying that it acts, forming 4 bonds, we would actually have to have the orbital notation for carbon look something like this over here on the right. 2s1, 2p3. We would need something like this. So how do we do that? These orbitals undergo something called hybridization. So again, still considering CH4, the carbon atom has 4 valence electrons with electron configuration helium 2s2, 2p2. Like we said before, you may expect the 2 unpaired p electrons to bond with other atoms and the 2 paired s electrons to remain as a lone pair. However, carbon, goodness gracious it does, carbon undergoes hybridization, a process in which atomic orbitals, right, in this case it's the 2s and the 2p, mix and form new identical hybrid orbitals. So with carbon, we take the 1s orbital, not the 1s, but the single s orbital, and then the 3 p orbitals that carbon has, and we mix them all together, and we separate them out into now 4 orbitals. Okay, we put 4 orbitals in, we got 4 orbitals out. However, now the result is a mixture of what we put in. We call these hybrid orbitals sp3 orbitals. And it is the presence of this sp3 hybrid orbital that allows us to have something like tetrahedral geometry. Remember, tetrahedrals when you have 4 atoms bonded to a central atom, like in the example of CH4 methane, which we're talking about right now. So note that each hybrid orbital contains 1 electron that it can share with another atom if we have 4 unpaired electrons. That will give carbon 4 bonding sites. The hybrid orbital is now called an sp3 orbital because the 4 orbitals form from 1s and 3 p orbitals. So when I say sp3, right? The 1, the superscript 1 on the S is assumed because it's the S is there. But the superscript 3 after the P indicates that there are 3 of them, right? 3 of them were put into the mix. If there were only 2, we would call that sp2. So let's take a look at that. Now, that's not the only hybridization that is possible. We don't have to throw all 4 orbitals into the pot to hybridize them. That does happen, and it results in sp3 hybridization. We're showing here on example A, or it's going to result in tetrahedral geometry. Anything with the tetrahedral geometry is a result of sp3 hybridization, and carbon is the most common example of that. But anything that has a trigonal planar shape, again, we should be a little bit familiar with that from our work last time in class, is a result of sp2 hybridization. Okay, sp2, we've taken the s orbital and we've taken 2 of the p orbitals and hybridized them. So we've only taken 2 of the p orbitals. Something like aluminum chloride and a nitrate ion are examples. Okay, of sp2 hybridization. What an sp2 hybridization allows you to do is form a double bond. Anytime that you're seeing a double bond, it's either sp2 or sp hybridization. But when you look over here, anything that has a linear shape, okay, anything that has a linear shape is a result of sp hybridization. Just a single s orbital and a single p orbital hybridizing together. Carbon monoxide and carbon dioxide are common examples. These often result from double and triple bonds. So when you see a triple bond, there's probably, most likely, some sp hybridization. So you can think about it that way. You can associate these different types of hybridization with those different shapes. If you're looking at something that's linear, there's going to be probably some sp hybridization. If you're looking at something that is trigonal planar, okay, you're going to have some sort of sp2 hybridization. And if you're looking at something that is tetrahedral, you're looking at something that is sp3 hybridized. So, lone pairs and hybridization. Lone pairs can also occupy hybrid orbitals. Not can, they do occupy hybrid orbitals. So compare the hybrid orbitals of beryllium chloride, which is linear, and then water, H2O, which is bent. Okay, beryllium coming in the second main group only has 2 valence electrons, so it's going to form a single bond to chlorine on one side, a single bond to chlorine on the other side. That's just linear. Yeah, that's linear. It's straight because there are no lone pairs. But when you look at water, that oxygen has 2 lone pairs. So that is actually going to experience repulsion between the lone pairs and the bonding pairs, right? The pair of electrons that's shared between the oxygen and each hydrogen. They're going to repel each other, and the presence of those lone pairs is actually going to push the bonded hydrogens down into a bent shape. So, why does the water molecule have sp3 orbitals and beryllium chloride have sp? Well, the 2 OH bonds in water occupy 2 of the sp3 orbitals in water. Well, that's only 2 of the 4 hybrid orbitals. There are 2 more orbitals left. Well, the lone pairs occupy those other 2 hybrid orbitals. Okay, sp3 orbitals, there's always going to be 4 of them because you mixed 4 orbitals together. So you're going to end up with 4 hybrid orbitals. 2 of those are occupied by bonding electrons. 2 of those are occupied by lone pairs. But when you look at beryllium not having any lone pairs, its geometry, there's nothing to occupy any, well, there aren't any other hybrid orbitals, and so there's nothing to occupy those. So it remains linear with sp hybridization. Now we're going to move on to intermolecular forces. Now there are 2 types of attraction in molecules. We have intramolecular bonds and intermolecular forces. Okay, we have already looked at intramolecular. Those are bonds. We looked at intramolecular stuff when we looked at ionic bonds, polar covalent, and nonpolar covalent bonds, even metallic bonds. When we talk about intermolecular forces, also known as IMFs, we're looking at the attraction between different molecules, okay? Different molecules, as opposed to the attraction of atoms within a molecule. Okay, like H2O. If we're talking about intramolecular forces, we're talking about the attraction between the oxygen atom and the hydrogen atom. Okay, that's intramolecular because it's inside that single molecule. But if we're talking about multiple water molecules and how they attract one another, that's intermolecular forces. And that's what we're going to look at right now. Now, IMFs come in three different flavors, three different types. We're going to look at dipole-dipole. Okay, that's one type, dipole-dipole interaction. Hydrogen bonding, okay, which even though it says bonding, it's not a type of bonding. It truly is intermolecular. And the last one we're going to look at is London dispersion forces. Sometimes just call it London forces, same thing. Let's start with dipole-dipole interactions. We have seen that molecules can have a separation of charge. Over here on the side we have hydrogen chloride or hydrochloric acid, however you want to look at it. You have a hydrogen atom, you have a chlorine atom. We saw that with regard to electronegativity, chlorine is much more electronegative than hydrogen. So these blobs, these dark blobs right here, represent electron density or the size of the electron cloud. This is a lot more dense, a lot larger. There's a lot more negativity coming out of chlorine, and we would expect that because chlorine is much more electronegative than hydrogen. So just looking at the sheer size of these dark splotches, we see that this end, the right side, the way it's depicted here, the right side, the chlorine side of HCl, is a partially negative charge, whereas the hydrogen side, the left side as depicted here, has a partially positive side by comparison. By comparison. And so this is what we mean separation of charge. We have a partial negative on one side, partial positive on the other. This happens in both ionic and polar covalent bonds. The greater the electronegativity, the greater the dipole. Okay, the greater the difference in electronegativity, the more violent that dipole is going to be, meaning it's going to be still partially negative, but a lot larger partial negative and a lot smaller, larger partial positive. Now, as a result of this, molecules can be attracted to that partial positive and partial negative. Regular old electrostatic attraction. Okay, still working with electrostatic attraction. So we have this bad boy, just like with the HCl we have represented up there. We have partial positive, partial negative, and that's what this symbol right here means. It just means partial, because it's not a true positive charge or a true negative charge. That would involve ions. So this is just partial. Now the negative end, the partial negative end of this, is going to be attracted to the partial positive end of this other HCl. And so there's going to be an attraction in this direction. They're going to be held together. We have maybe something else, and we have multiple forms of attraction. The more we add molecules to this scenario, this dynamic multi-directional attraction takes place between the oppositely charged, partially oppositely charged ends of these molecules, these dipoles. And again, dipole, just di referring to two poles, referring that has poles. There's a positive pole and a negative pole. There's two. Hydrogen bonding, next up. Now, hydrogen bonding is not bonding. That is an intramolecular attraction. We're talking about intermolecular forces here. Hydrogen bonding is actually a special type of dipole-dipole interaction that is especially strong. The way you can know that you're looking at hydrogen bonding is that it only occurs between a few different atoms. It occurs between highly electronegative elements. Okay, those are nitrogen, oxygen, and fluorine. If any of those three are interacting with hydrogen, that's a hydrogen bond. Okay, if it's a dipole-dipole interaction between hydrogen and then a nitrogen or an oxygen or a fluorine, we're going to consider that hydrogen bonding. Now, an example question to prove the point here: calculate the difference in electronegativity for HCl and H2O. So, if I calculate electronegativity in HCl, okay, I look up the electronegativity for hydrogen and chlorine, I get a difference of 0.8. If I do the same thing for water, okay, I have the electronegativity of oxygen coming in at 3.5, hydrogen coming in at 2.1. Difference is 1.4. This high electronegativity difference between the oxygens and in this case the oxygens and the hydrogens, creates a situation in which those two atoms are still bonded. Okay, the oxygen and the hydrogen are still bonded, but the electrons in that bond are very, very, very close to oxygen, making the extent of that partial negative charge much, much larger. Okay, it's a much more extreme partial negative charge. It also makes the partial positive charge on the hydrogen much more positive, much larger in magnitude. And when you make a partial negative charge or a partial negative charge stronger, you're making the attraction that they are going to experience stronger as well. And so functionally, we see that hydrogen bonding ends up being about 5 times stronger than your average dipole-dipole interaction because of the extreme difference in electronegativity. All this jazz is given a special name, hydrogen bonding, because the compounds containing these bonds are very, very important in biological systems. Okay, we're not just giving it a special name so we can have more to study. This is very, very important when studying biology. And the last type of intermolecular force we're going to look at, London dispersion forces. Now, when you have nonpolar molecules that don't have dipoles like polar molecules do, how then can those nonpolar compounds stay as solids or liquids? Well, there's a guy named Fritz London. He described these London dispersion forces, which are also known as van der Waals forces, if you hear that term maybe in college somewhere else. These London forces are due to small dipoles that exist even in these nonpolar molecules. Even though they are truly nonpolar, there are small, what we call dipole moments. Because electrons are moving around in atoms, okay, think of those electrons moving around the nucleus, there will be instants, and I emphasize instants, where the charge around the atom is not symmetrical, right? The electrons are not perfectly spread out, evenly spread out around that nucleus. Now, it's only going to be for an instant, but this results in a small dipole, small partial positive, small partial negative, but now we have the basis for electrostatic attraction between atoms and molecules with whatever this compound is. Now, we can have we have what we call instantaneous dipoles, okay? We got this going on. We have all these electrons spread out. And they're just moving. They're just moving. Now, if they randomly, like that, if they randomly, just for an instant, eventually, as those electrons are moving around that nucleus, eventually electrons are situated so that a small dipole forms. Notice that in what I have drawn here, most of the electrons are on the right side of their molecule. So that creates a partial negative on that side and a resulting partial positive on the left side. Now, this only exists for the tiniest of times, okay? But it is enough to generate electrostatic attraction. Now, that was just instantaneous. It just happens for a moment. So we have our situation here. Stuff's moving around, stuff's moving around, stuff's moving around. We have this situation where we have an instantaneous dipole on that left one. And so notice those electrons are lined up mostly on the right side of that figure, okay? And what that does is it forces the electrons on the thing on the right to line up accordingly, because since that instantaneous dipole created a partial negative on this side, it's going to repel the electrons in this right molecule and send the electrons in that molecule to the right side as well. So we call this an induced dipole. So dipole forms in one atom or molecule, inducing a dipole in the other. All right, guys, that's going to do it for this part of the video lecture. I will see you next period.